Okay, so yeah, there'll be some applications of the things that we've talked about. I consider this, I guess, if you will, an application. It's it's almost a definition, but anyway, find the equation of a tangent line. If you've got your function, well, first of all, we're talking about a line, so equation of a tangent, I'm looking for y equals mx plus b. But what calculus brings to the table here is if it's a tangent line, then my slope is, it's going to be the derivative, right? That's, again, like I said, that's just a very definition. The derivative of a function at a particular value, that's equal to the slope of the tangent line. So that's what we're looking for here. Is first of all, we're going to do the derivative. So my derivative is 6x minus 5. I want the tangent at 2, 6, and so the x value I want the tangent at is 2. So the slope of this line is going to be the derivative at 2. So that would be 12 minus 5, 7. So the slope of my line is going to be 7. So that's the m in the y equals mx plus b. Now I just have to figure out b. And the way I did it is now we can substitute the x and the y value. The y value is 6, so plug that in with the x value 2. So that's 6 equals 14, so subtract 14. B is negative 8. So there's my tangent line. And so if we graph the function and in this line, we should see that it's tangent. That line is tangent at 2 to that function. But that's, I call it an application, but one thing to remember, yeah, the derivative equals the slope of the tangent line. All right, number 9, what I've got there is a question about the critical numbers. Well, yeah, we saw that certain things happen at these so-called critical numbers, and so those critical numbers are important to find because, well, for one thing, they give you where maximums and minimums occur, one thing. But as far as critical numbers go, we've got two types, right? Two types. We can have a critical number where the derivative equals 0, or where the derivative also does not exist. So, if you're finding the critical numbers, find if they exist, where the derivative equals 0 and derivative does not exist. Well, of course that means here I need to get my derivative, and how would I get the derivative of that? Well, that's probably, again, rewriting it a little bit. Isn't that 9 minus x squared to the 1/2 power? And so my derivative here, it's again another chain rule, a little bit of chain rule. Got an inside and outside part. The inside is 9 minus x squared, the outside is the 1/2 power. So do the derivative of the outside, so it'd be 1/2. Inside stays the same, 9 minus x squared. New power, subtract 1, we minus 1/2. Then we have to do the derivative of the inside, which is negative 2x. So let's clean it up a little bit. The 2's will cancel there, so the top will be a minus x. Let's go ahead and write it this way. Top will be minus x, and then since that's a minus 1/2 power, flip that over, it'd be the square root of 9 minus x squared in the denominator. So that's my derivative. Negative x over 9 square root of 9 minus x squared. Okay, so first of all, set that equal to 0. Which that's going to be a pretty easy one. to solve that, just multiply both sides by the square root of 9 minus x squared. So that'll cancel that out. We just have minus x equals, and that's still 0. So that's just x equals 0. So this one does have a critical number of x equals 0. Now, the does not exist, well, the derivative does not exist at a couple of places, but for these, usually what we're looking for, unless it's an absolute value or something like that, the does not exist is, what are we looking for there? Denominator equals 0. It's usually what we are trying to find. So I just set the square root of 9 minus x squared. If I need to, just set it equal. Sometimes you can just eyeball it in, but I'm looking for, yeah, denominator equals 0, so that's why I wrote it like that. Which, yeah, if I square both sides, I'll get 9 minus x squared equals 0. So that's 9 equals, add the x squared. Square root both sides. The only catch is it can be plus or minus square root of 9, so it's plus or minus 3. So those are my critical numbers. I have to find those come finals time. Another application I got here on number 10. All right, so we got the volume of a sphere is increasing at a rate of 8 centimeters cubed per second. The rate of the radius is changing. Oh, at what rate is the radius changing? When the radius is 80 centimeters. Note the volume of the sphere. Yeah, on these volumes or surface areas, if I use a volume or surface area formula on the test, I'll provide those. You don't have to memorize the volumes and surface areas. You know, if it's area of a rectangle or area of a circle, you need to know those, the basic equations, but volume and surface area, I'll give you those formulas. You don't have to memorize those, but make a note of that. But what I would say on number 10, what we've got there, so it says the volume of a sphere is increasing at a rate of 8 centimeters cubed per second. What we should note there is what that gives me, that's not the volume is 8, right? That's the rate at which the rate is changing. So that's another example of an application of derivative, isn't it? Derivative equals slope, but it also, derivative is, it's a rate of change for a function. And so when it says the volume of a sphere is increasing at a rate, that's the derivative of the volume. The derivative of the volume with respect to t, or dv dt. dv over dt is 8 centimeters cubed per second. That's what that gives me. And so what I'm looking for, it says at what rate is the radius changing. So I'm looking for there the rate the radius is changing with respect to time. So I'm looking for dr over dt, right? When the radius is 80. So the given ones I'm given, those two, and then I'm looking for dr over dt. So back to my formula here. Volume is 4/3 pi r cubed. That's for the volume of a sphere. So I'm trying to find dr over dt. So what do I need to do to this function, equation, to find dr over dt? Well, I need to take the derivative with respect to t of both sides. I need a ddt, we call it both sides here. Take the derivative with respect to t of both sides. Now, doing the derivative with respect to t, so by power rule, derivative of v would just be 1, right? However, I'm doing the derivative with respect to t, so I would need a dv over dt there too, right? Remember that? Now over here, 4/3 pi is just a constant, so I can just bring it along. Then I can do the derivative with respect to t of the r cubed, which is 3r squared, power rule. But I'm doing the derivative with respect to t, so I'd also need a dr over dt with that. then once I got that, then usually the next step is just plug in what you know. All right, so here we've got dV over dt is 8, so this side's 8. We got, 3's canceled, so this is just 4 pi times the radius squared, so d times 80 squared, and then dr over dt, that's what I'm looking for. Go ahead and multiply these, that'd be 4 times 80 squared, 6,400, what is that? 256,000. 25,600 actually. So the 4 times 80 squared is 25,600. So to find dr over dt, I would just need to divide by the 25,600 pi. That's my dr over dt, my rate change. Different ways to write that, but let's just round it here. It's not a very big number for sure. It's 0.00 4 zeros and then 9947. Mine's given in scientific notation. Now that also brings up, what are the units here of dr over dt? Well, the units of the derivative are going to be the units of the r over the units of the time. So, well, the radius comes in centimeters, isn't it? So the units of the radius would be centimeters, and then the units of the t would be time, which is seconds, I believe, right? Yeah. So it's about 900 thousandths or something like that. Thousandths, 10. Yeah. Not a very big number, but is that all right? Good on that? Okay, got a couple more here. All right, so a farmer has 500 feet of fencing divided into 3 pins like this. So I've got fencing is 500 feet. It's a rectangle divided into three pins like this. Okay. So what are the dimensions that would make the largest possible total area for the pins? All right, so the best way here, I need, first of all, I need a formula or an equation. Best way to do these, instead of looking at it as 3 pins, is just look at it, as far as area goes, you just got a x by y dimension rectangle. So the area is just x times y. Now, I want to maximize that. Well, that's where our critical numbers come in. Like I mentioned earlier, critical numbers are usually where the maximum or minimum for a function occurs. And so when it says find the maximum, that's usually what we're looking for, is a critical number. Well, the critical numbers are all about the derivative, right? Derivative is 0 or derivative does not exist. And for these, it's usually where the derivative equals 0. So what I need to do is find the derivative of this thing. The problem is, this function, I have 2 variables, and we hadn't talked about how to do derivatives of 2 variables, functions with 2 variables yet. So we need to get this down to a 1 variable function, and the way we do that is with the fencing here, and that's where the pins, if you will, come in. So the fencing here, I've got, notice, if I fences like this, I've got 2 x's, and then I've got 1, 2, 3, 4 y's. And so I'm going to use that equation. Well, the fencing is 500, so 500 equals 2x plus 4y is the other equation here. And so usually when you have the two variables, that's what it means. You've got another equation that has both variables, so you can eliminate one of these variables by using the other equation. Well, in this case, you can do it either one, but it looks like it's going to be easier to solve for x here. So let's subtract 4y. 500 minus 4y equals 2x. Divide by 2, so that would be 250 minus 2y is x. Yeah, so I can get rid of one of my variables up here, the x, by using that fencing equation. So area now is 250 minus 2y times y is my area function now, which is just one variable function. So if I distribute 250y minus 2y squared, that's going to be an easy derivative, isn't it? So again, I'm wanting to maximize which occurs at the derivative, so take the derivative. So it'll be 250 minus 4y. Like I said, this one, usually the critical number you're looking for is equals 0, so set that equal to 0. Add the 4y, 250 equals 4y, divide by 4. Was that 62.5 is y, is that right? What was the question? What are the dimensions that would make the largest? Okay, so our maximum area is going to occur when y is 62.5. That's what this is saying. I mean, we didn't check it, but that's just how this will work. That's going to give us the maximum area. Now, the other dimension I would need the x. Well, the x would be, just have to solve our little formula there when y is 62.5. So plug in the y to be 62.5 in the x equals equation there. I believe, yeah, that's going to be 125. That's feet. Remembering right there, it's feet. 500 feet. Oh, yeah, that's right. So that would be the dimensions to make this the maximum that could occur. You can check it, but that's where the maximum will be. All right, question? Is that okay? All right. Number 12. At 8 a.m., ship A is 50 miles east of B, so I've got the diagram there. Ship A is sailing south, and ship B is sailing west, so that's south and this would be west at 25 miles per hour. So let's call this X and this Y, how far they've sailed, and what we want to know is how fast is the distance between them changing, and we called it Z. I mean, we could call them other letters there, but that's the way we normally did it. Yeah, so we've got ourselves here, formula-wise, the Pythagorean theorem, don't we? Y plus 50 squared plus x squared would equal z squared. Well, here's what we want to find. How fast is the distance between them changing? So I want to find how fast is that distance between them changing. So I'm looking for dz over dt, the rate at which z is changing. I've got the rate x is changing, which is a. So dx over dt is the rate a is changing, which is 20 miles per hour. And then the rate at which y is changing is dy over dt. That is b's speed, which is 25 miles per hour. So I've got those. And I've got the time is 8, it goes from 8 to 11, so the time is 3 hours. let's see how we do that. So that's what I'm looking for, dz over dt. So I've got to, again, d dt both sides. Take the derivative with respect to t of both sides. And so this one, little chain rule, will be 2 times y plus 50 times the derivative of the inside would be dy over dt. 2x, again, doing the derivative with respect to t, so you need dx over dt as well for that, and that equals 2z dz over dt. On the right side, and yeah, those always, in this particular case, come out with 2's in the front, so divide everything by 2, so cross out the 2's. So that's what we need to solve to find dz over dt. Now, we've got dx over dt and dy over dt. I'm looking for dz over dt, but we need the x and the y and the z. Remember the x is just how far a has traveled, so that's just the rate times the time. So the rate is 20 times the time is 3, so that'd be 60. The y would be its rate, which is 25, times the time, which is 3, so it's 35. But we still also need z. Well, I don't have a z rate times time for that, but I do have this equation, which now I can plug in my x and my y and find the z, can't I? So do the y plus 50, so that'd be 75 plus 50 squared plus the x squared, which would be 60 squared, that equals z squared. Yeah, solve that out there and find your z. So 125 squared plus 60 squared is 19,225. 19,225 is z squared. So z would be the square root of that, 19,225. So that's what we're going to plug in for z. Yeah, so now we've got all the stuff to plug in. So plug in y, 75, plus 50, times dy over dt is 25, plus the x, 60, times dx dt is 20, and z is the square root of 19,225, times dz over dt. So now it's just multiplying, adding, and dividing. 125 times 25 plus 60 times 20. This side's going to be 4325. And then we're going to divide off the square root, 19,225. That's dz over dt. I get 31.19. You guys get that? Miles per hour? Is that okay? So that's all of them on the sheet there.